We have alerted government stakeholders, especially in the defense and intelligence communities, about this demonstration. We view us as a white hat party. It's better that we're doing this fundamental work rather than malicious actors, and that post-quantum standards will be better prepared, better aligned with what the threats are if they know the extent of the threats.
For the first time ever, Shor's algorithm is running on logical qubits. The team at Infleqtion used their Sqale, with a Q, neutral atom processor to accomplish the feat. While the setup only uses 6 logical qubits, and we're still in the range of factoring 15 or 21, this is both a proof of concept and a proof of the need for PQC. We discussed the aggressive 2.5 to 1 physical to logical ratio of Sqale, and the shocking idea that running Shor's algorithm could end up being one of the first killer apps for quantum computing in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is a repeat guest. He's the Senior Quantum Solutions Manager at Infleqtion. Peter Noell, welcome back to the Post-Quantum World.
Thanks, Konstantinos. Great to be back.
Yeah, and I like to have people back on, sometimes to catch up, and sometimes because there's a big breaking announcement. So this is going to be a little bit more on the breaking announcement side. So I'm just going to tell everyone and then ask you the details that you were able to run for the first time Shor's algorithm on logical, not just physical, logical qubits. So, there should be all sorts of fanfare and balloons falling right now. So I'll let you tell us a little bit about that.
That's right. Yeah, thanks for that intro. And that is right. That Infleqtion's quantum computing team, we've run the first ever demonstration of Shor's algorithm using logical qubits on our neutral atom QPU named Sqale, with a Q, of course. This was, I have to caveat that it was a pre-compiled, non-scalable version of Shor's algorithm, but it's a nice target to demonstrate and test new capabilities that will be critical to a future scalable version demonstration. So, as I'm sure many of your listeners are aware, Shor's algorithm is perhaps the most famous quantum algorithm. It allows one with a powerful enough quantum computer to factor an integer into its 2 primes, and it can do this exponentially faster than a purely classical algorithm. And this is, of course, important because many cryptographic standards are based on the assumption that it's easy computationally to multiply 2 primes together, but very difficult to do the reverse, that is to factor them back into the 2 primes. So we view this demonstration as the first domino to fall toward cryptographically relevant quantum computation. And there have been several prior experiments running Shor's algorithm. Historically, though, they've all been on physical qubits, not logical qubits, as you mentioned. So physical qubits aren't really capable of realizing Shor's algorithm at meaningful scale. And so as quantum computing transitions into the fault-tolerant era from the NISQ era, we view this as that first important domino to fall in an upcoming line of experiments. And just as a refresher, physical qubits, in the case of neutral atoms, are individual atoms trapped in a 2-dimensional array by laser. And they're cooled because the laser stops the motion, no cryogenics are required. And so the logical qubits are the result of stitching together more than one physical qubit and encoding the information so that the logical qubits perform better than the physical qubits. And by perform better, I mean that they produce errors at a significantly lower rate than the physical qubits alone. So it's a trade-off, ultimately, of qubit quantity towards qubit quality. And so what we've done here is we've shown better logical than physical performance, achieving that trade-off that we seek. So that's really where a lot of our exciting results lie, and much of what I want to discuss today, in addition to the broader implications of Shor's algorithm and what the outlook is today, given our results and other recent exciting results.
Yeah, some great points and a lot to dig into, which we're going to, of course, do in this episode. So first off, about where are we right now in the physical to logical ratio with the approach that Sqale uses with a Q?
So this demonstration was on 6 logical qubits on our Sqale machine. So in our demonstration, we used a logical encoding called an iceberg code. And this builds on prior fault-tolerant quantum computing work that we've done with JP Morgan Chase, for example. We earlier this year published a library of codes called QLDPC. And
Mm-hmm.
there are many reasons to like the Iceberg encoding scheme that we use, but the biggest reason that we chose it is because it has very favorable scaling. Up to this point, a different encoding scheme called the surface code has been the current code of choice for modalities like superconducting, but surface codes are undesirable for the reason that they require many physical qubits per logical qubit, with many being as much as like thousands of physical per logical qubit. So they're great. Surface codes are great. They're hardware friendly for much of today's hardware. But our Iceberg code, to answer your question, only requires 2.5 physical qubits per logical qubit. So that's why we see these results as a big first step toward experimental realization of Shor's algorithm at meaningful scale, even though this is on the so-called non-scalable precompiled version of the algorithm.
2.5 is kind of crazy.
But
I
yeah,
mean, like, I don't think we hear that ratio ever. That's pretty aggressive.
that's why I think the discussion around Shor's algorithm is very dynamic, very always evolving, because it it can change from something like the order of thousands as an estimate per logical qubit to just 2.5. So there's a lot of variability depending on many factors, qubit modality, et cetera. And just to be clear, the Iceberg code is an error detecting code. So it's not full error correction quite yet. So error detection means that we don't correct the errors, we just throw out the bad results. But if you concatenate Iceberg codes, you can turn it into a error correction code ultimately.
So how would you see this scaling with Sqale, like with this general approach? Would it have to completely change?
Yeah, so it scales in that ratio of 2.5 physical qubits per logical qubit. Looking at our scale roadmap right now, well, I guess last year in 2024, we announced 2 logical qubits for a material science application with NVIDIA, which we were really excited about. And we've actually accelerated our roadmap forward, and we're aiming for tens of logical qubits, hopefully by year's end, but at latest end of 2026. And we're targeting hundreds of logical qubits by end of 2028. Depending on when this podcast airs, we will we'll have a new roadmap to unveil in the near future too.
So if you look at the Gidney paper, the idea there is around 1,400 logical qubits, let's say, to run Shor's algorithm against RSA 2048. With your predictions and projections for how your roadmap will scale, when do you see your approach hitting something like 1,400 logical qubits?
Yeah, I don't know if I want to put a specific date on
Mm-hmm.
1,400 logical qubits necessarily, but I think that the big takeaway is that it really is in the not so distant future, and there's a lot of reasons not to panic, but to start preparing. I don't want to incite panic with these results. I don't think that's a takeaway anyone should have from this. But you're right. With
I want to incite
yeah,
panic
of
because I don't
course.
think anyone's moving fast enough. If I'm being frank,
That's part of
I
your
don't mean
agenda.
fear mongering sort of way. Yeah, I mean
Exactly.
no one's doing anything about this really, relatively.
No, but exactly. But in all seriousness, it does underscore some urgency. No need to panic, but some urgency needed. And you're right, with the Guinea results earlier this year, that paper was a 20x reduction in the required qubit count from 20 million down to under a million to run Shor's algorithm to break RSA 2048. So I think you can anticipate our work here, or you can view that as a step change towards realizing this in a practical sense. And if you do the math with qubit quality and qubit count and gate speeds of Infleqtion's roadmap and other roadmaps, you can see that there is line of sight to where this is real, but it's not super relevant for an exact date of when it will actually be broken. But just the fact that it is within 5, 10, 15 years that we have that line of sight, it is important to start preparing, because it isn't just RSA 2048 at play. There's elliptic curve cryptography, which is uh, the cryptography scheme used by Bitcoin, Ethereum, other cryptocurrencies, and that will require significantly fewer quantum resources to break. So that's even closer. And if you can break elliptic curve cryptography, then one in principle could steal cryptocurrency. And the whole premise of Bitcoin, at least by some accounts is that it's stable and secure for years to come. So if there's this vulnerability, that's a huge issue. I think Bitcoin's market cap is over $1 trillion. There are massive implications of this to the value of crypto. So
Yeah,
some
because you're not
cryptocurrencies
stealing only; you're making everything worth zero
worth zero, exactly.
overnight, potentially. Yeah.
It's critical. The security aspect is really critical to the whole premise of cryptocurrencies like Bitcoin. And I think a paper came out last year out of the UK that estimated that it would require months, I think over 2 months, 76 days of downtime to upgrade Bitcoin to post quantum cryptography. So it can be solved, but it's going to be a headache, and it's going to take some time and planning, and something that needs to be thought about now rather than when this gets imminently close. And that's all not even to mention the harvest and hold style attacks that folks in the industry like to talk a lot about, where adversaries can store data now and decrypt it at some point in the future, that with the hope that the information is still relevant. But it is good to see there are positive signs. Like, I remember when my iPhone updated a year or two ago, or whenever that was, and it mentioned in the update that iMessage was upgrading to PQC standards. But so it's good to see that steps are being taken, but we don't even have assurances yet that post quantum crypto is totally robust against quantum computing. So it's something that needs to be given a lot more attention, in my view.
Yeah, that Apple move to what they called PQ3 was their first major stab at that.
Yeah.
It was pretty aggressive, the constant changing of keys and everything. So you mentioned earlier that it takes less quantum computing horsepower, basically, to crack elliptic curve. What's your latest guess on how that Bitcoin kind of cracking range is compared to RSA?
I don't know if I can put an exact number on it per se, but I think the results that we have here are some core fundamental capabilities that will be used when that day comes. For example, another capability that I haven't addressed yet is called individual addressability. So suppose you're sitting next to your desk mate at work and you want to talk to them, but in order to do so, you have to go to the conference room, talk to them, and then come back to your desks. And imagine you have to do that a million times per day. That's what happens in a lot of cases with some of these codes. You have to move qubits to an entangling zone, which, if you do that a million times, that eventually gets very, very slow. So the logical qubit results that were published about a year and a half ago out of Harvard, they implemented this atom motion that did this. It moved atoms to an entangling zone, and it had all these advantages. It was a great demonstration of logical qubits. But the big bottleneck there was that this takes a lot of time. So the bottleneck up to this point has been speed. And then in contrast, we've had this in place static entanglement before. IBM machines have had this for quite a few years, but not motion. So in our results here, we sort of have the best of both worlds. So the atom motion allows us to do some important fault tolerant initialization that we otherwise wouldn't be able to do. But then we can do this in place entanglement. So we have the qubit quantity. Neutral atoms have always been very strong there because of the scaling in 2 dimensions. And in recent years, they've caught up in terms of qubit quality. Infleqtion has a 2-qubit gate fidelity record of 99.73%. And the bottleneck up to this point has been speed. So this demo was only really possible recently because of these metrics and overcoming the speed bottleneck. And this is really what's helping us along, and the reason why we're saying that this is a step change toward realizing Shor's algorithm at scale. So that's one really cool aspect of it. We're going to need more sophisticated error correction codes to maintain the scaling advantage. We're going to need things like mid-circuit measurement, hardware upgrades, iceberg code concatenation, et cetera. But it's a really important step here. And the other aspect to these results that I haven't mentioned yet is that this is actually a part of a broader research collaboration with UT Austin that identifies how to optimally chunk programs into logical qubits. So when you have logical qubits, there are a lot of ways that you can map physical qubits to logical qubits. And so our partners at UT Austin, the Baker group there, they looked at ways to optimally assign them. So back when superconducting qubits and surface codes were the only game in town, the rule was that each one patch of physical qubits would equal one logical qubit. But with neutral atoms now and this atom motion, we can have many logical qubits per patch. So we have this interesting assignment problem of how to do this optimally. And it's all enabled by movement and connectivity of neutral atoms to do these more interesting codes.
So you've said that, like, not in this recording, but
Yeah.
but you guys have been talking about how Shor's algorithm might be one of the first utility scale quantum computing applications. That might come as a surprise to folks, right? Like, everyone's just been trained to think, oh yeah, cracking encryption is the last thing we're going to do. It's going to be a million other things first, change the world. You know, we're all going to live in this utopia, and then we're going to start cracking encryption.
Yeah.
Do you want to touch on that a little bit?
Yeah, and I don't think that view is totally uninformed. You know, in 2022, there was a paper called "Assessing the Benefits and Risks of Quantum Computers" with a lot of
Mhm.
high profile authors on it. Very credible source that determined that economically impactful applications would come sooner, most likely, than cryptographically relevant sorts of applications. But I think since
Mhm.
2022, there's been a lot of ground that's shifted quite considerably and has changed our view, at least in this regard. So one result that's changed since 2022 is, as you mentioned, the Gidney results going from 20 million qubits required to 1 million qubits or even fewer for the
896K, I think. Yeah, something like that. Yeah.
exactly.
Mhm.
So I think that's one big thing that's changed. Another is really the emergence of neutral atoms in general and their ability to implement these really cool, highly scalable codes like the ones I've talked about today. So thinking back to where the industry was in 2022, you know, there was still a lot of hope for the NISQ era type computers. It was mostly about superconducting computers and trapped ions. And neutral atoms have really come to the forefront and emerged from dark horse status to sort of the forefront of the industry. So I think that's another change, and the implications, the underlying work that goes along with it has changed the math there as well. And then I think there's also the third thing I would put along with this is the one big drawback that people always talk about with neutral atoms is the slow gate speeds, and a lot has been overcome since then in terms of speed ups like transversal gates and mid circuit measurement. Again, things that you can do with neutral atoms more readily than other modalities. So I think the thinking has changed considerably since then, and this is something that government, companies, institutions need to be thinking about because it is closer than it appeared 3 years ago.
Yeah, I think just last May it was like a 50x speed up, right, in transversal gates.
Yes, exactly. 50x.
Yeah, so that made a huge difference.
Yep, that's a massive. That's even bigger than the 20x from the
Yeah,
20s.
yeah.
Exactly.
That's true. And you know, when you talk about your process a little bit, it reminds me almost of like what's starting to happen in things like the Gidney paper. This like creative way of having like scratch qubits that you can use and that sort of thing, like trying to constantly refine the approach. There could still be more refinement still to Shore, right?
Definitely.
It's possible within this next year that we'll see something else that'll be terrifying.
Definitely. And maybe this, going back to an earlier question of, you know, how long until we break RSA 2048 or elliptic curve. This is sort of how I think about where we're at. So as I mentioned, there have been prior demonstrations of Shor's. Some have been this unscalable version where you have some implicit knowledge of what the factors are.
Mhm.
And it seems like maybe there hasn't been much progress made given that 15 and 21 are the only numbers that have been factored by any version of Shor's algorithm. But I think that's an incomplete view of where the progress is and the outlook, and it disregards a lot of this underlying fundamental work that's going to unlock a lot of progress here in the coming years. So, at risk of oversimplifying things, this is how I sort of think about where we are with Shores. So, if you can picture a plot where the x-axis is the number that you need to factor, and the y-axis is the difficulty of factoring the number into primes. If you were to draw a curve for a classical computer, you would make the y-intercept 0, meaning that for very small numbers, classical computing can factor these quite easily. But moving
Mhm.
along the x-axis to relatively modest number sizes, relatively doing a lot of work here because these are obviously very large numbers, the curve gets very steep, and it gets very steep very quickly in the grand scheme of things, meaning that the computational complexity gets very big very quickly. So on the same plot, this is how I would overlay a quantum curve. You have your y-intercept, and that would be relatively high, higher than zero for sure, indicating that there's substantial overhead needed just to factor small numbers like 15 and 21. But if you plot the rest of the curve, it increases much, much more gradually than the classical curve because the complexity scales with the number of digits roughly rather than the absolute size of the number that you're trying to factor. So all this is to say that we're on the cusp of moving, we're kind of climbing up the y-axis towards the y-intercept on the quantum curve. And I'd say we're on the cusp of moving past it onto the quantum curve, and that from here it gets much easier, not in the sense that this is going to be an easy task to break any sort of cryptography, but that's where I'd say we are. And the logical qubit implementation of the unscalable version is an important first step in our view. And the next step will be moving into the scalable version. And from there, we'll have a scalable algorithm, a scalable version of Shor's, a scalable logical qubit implementation that I've discussed, the 2.5 to 1 physical to logical qubit ratio. And I think progress will get a lot more noticeable and faster. Again, it's really hard to put a rate of progress once we get onto that curve, but I think it's going to get a lot more noticeable here in the next 5 years or so.
It sounds like something that's attainable. You're going to have computers improving with scale, and then you need a scalable Shors that you're running. So what's the next big hurdle to get to that first scalable implementation of Shors?
I think the hurdles that we'll need to overcome are better hardware, a few more qubits that are of extremely high fidelity, and then from there, it's implementing this algorithm. So the non precompiled version. We have some in-house expertise. Actually, I'll give a shout out to Rich Rines, who's a senior software engineer on our quantum compiler team. He was the co-author of a 2015 publication out of MIT. I think it was in Science, called Realization of a Scalable Shor Algorithm. So he and the rest of our team have done a lot of resource estimation and planning for how we do that with logical qubits next. And I can't put a specific date on when exactly that'll be, but that's definitely in the roadmap for Infleqtion to demonstrate.
So once we have the algorithmic work done on Scalable and your scalable machine, do you anticipate then kind of annually being able to say, look, we're up to this level, this bit number, like I kind of like something that you're keeping on the wall almost as this doomsday clock that's like approaching?
I don't know if it'll be an annual cadence, but I anticipate there will be some cadence of updates for what our capabilities are. And I want to be clear that, again, it's not our intent to cause havoc with any of these demonstrations.
Yes, of course.
We are primarily focused, really, as a software group on applying quantum computing for societal benefit, like machine learning, simulation applications, and so on. But we have been communicating and have alerted government stakeholders, especially in the defense and intelligence community, as well as various Congress people, about this demonstration. So we view us as a white hat party per se here, and it's better that we're doing this fundamental work rather than malicious actors, and that post quantum standards will be better prepared, better aligned with what the threats are if they know the range and extent of the threats.
Yeah, and Infleqtion does work with the government, right? I don't know if you want to just brag a little bit about a couple of the government things you have going on.
Sure. Yeah, I'll gladly do that. Yeah, it's been an exciting year. We've had a few big announcements. The one at the front of my mind as a Chicagoan is the announcement we had with the state of Illinois back in July. So we announced a $50 million private-public partnership to increase our workforce here up to over 50 people. I think we're at about 15 right now. So we'll increase headcount by at least 35 in the coming years, which I'm very excited about to grow here. So very excited about that. Another big announcement that we had earlier this year was a award that we had from ARPA-E. So it was ARPA-E's first ever quantum award, and actually the largest award of the batch that it was from. It was over $6 million. So that particular award is around the unit commitment problem, modeling that. on a quantum computer, specifically our Sqale computer again. So power grid optimization gets really challenging, especially with renewables in the grid. Planning to meet a anticipated customer demand gets very tough, and doing that at minimal waste, minimal cost is a very hard combinatorial optimization problem. So I'd say our day job is more focused on things like that rather than a Shor's demonstration, but this will be something that we'll be updating regularly, I would anticipate.
And if you do end up in the tens of, or let's say 100 logical range by 2028, I've got to believe there's a lot of commercial applications that you'll be tackling with that amount of power.
Definitely. I think we have a really strong focus in a few key areas. Number one, I would say is national defense security broadly, which could encompass things like energy. So the ARPA-E award that I discussed.
Mm-hmm.
We also have some great team expertise on material science. So looking at different applications there, for example, simulating strongly correlated systems. And then another one that we're really excited about is in life sciences. So our applications team has been working on and is currently in phase 3 of the Quantum for Bio project through the Wellcome Leap Foundation. So we've implemented a really cool algorithm there for feature selection. That's really the heart of the quantum algorithm. It's a hybrid algorithm, but the quantum part is focused on feature selection on cancer data. So you can imagine that with cancer data that has different features like RNA and DNA, there are tens of thousands of features, aspects of the DNA that have varying levels of predictability on the origin and nature of cancer within some tissue, but you have relatively few patient samples. So it's an example of data that is a good fit for a quantum computer because the features map one-to-one onto qubits. And it's, some people sometimes talk about how small data, but big search space is a good fit for quantum computers, and big data is sort of hard to map onto quantum computers. That's the underlying idea behind the algorithm there.
Yeah, a lot of times people, with what you just said, people just assume that a lot of these use cases are only going to be AI.
Yeah.
And do you think there's some kind of similar inflection point? It's okay to use that word if I spell it differently, right?
No, of course.
Yeah. Like with the XY axis discussion we had before, do you think there's something like that to be said for the future of competing with AI, like certain types of machine learning problems or whatever that quantum might be better at?
Yeah, that's an interesting question. I think we talk a lot about internally about quantum for AI and then AI for quantum, and using one to improve the other, and vice versa. I think that they will be complementary in a lot of ways. We have some interesting work called contextual machine learning that I would say is, to go into great detail, is probably a conversation for its own podcast. But that's around using quantum. A lot of the work we've done in true quantum computing for quantum inspired machine learning, which I kind of hate the term quantum inspired. It's been beaten to death, but it truly is quantum inspired in the sense that these AI machine learning methods that we've used and have now implemented on NVIDIA GPUs are truly born out of the work that we've done in the exploration research in quantum computing. So I think that's a good example of where they don't necessarily compete, or they sort of meet. But yeah, it's sort of hard to tell how that will all play out, because unlike Shor's algorithm, which has this proven exponential advantage, a lot of times in AI and machine learning, it has this black box characteristic where it works and it's not very explainable, but we just know it works. So that makes it harder to put predictions on what those curves will look like, versus I think we have a better idea with Shor's algorithm, as I outlined, what those curves look like.
Yeah, black boxes come up a lot in both AI and quantum, basically. Just dig into Grover's and you'll get plenty of black box action there with the Oracle.
Exactly.
And because we talked a little bit about cracking encryption, do you have any thoughts on the future of using Grover that way? It seems like everyone's I don't know, everyone's attention shifts away and to Grover. It's like, no provable path forward. It's not feasible. And then a few years later, it's like, wait a minute, we might be able to, it just like keeps coming back and forth. What are your latest thoughts on Grover's?
Definitely. I think Grover's algorithm is certainly interesting. I don't view it as near term as Shor's. Like we talked about how Shor's just keeps moving further to the left. It's getting closer and closer.
Hmm.
I think not the same is true of Grover's because of this overhead that you incur, in addition to it only being a quadratic speedup over classical, where you have this super polynomial speed up with Shor's that just has a lot of benefits to making it usable sooner.
Yeah, my take with Grover is it's such a simple thing to protect against. Just bump up symmetric to 256-bit and you're good, you know?
Definitely.
Because keeping 128-bit symmetric encryption means there's a real chance that one day that's going to be, all intents and purposes, 64-bit, and that's a nightmare. Like, why would you want to put yourself in that situation,
Yeah, and that's not to knock Grover's algorithm. I think it's useful and probably more versatile, you'd say, than Shor's, and definitely worthy of further investigation, even in the near term. But it's not as much our focus at Infleqtion.
Okay. So I'm pretty excited about the new roadmap, and I know there's going to be more buzz generated as you reveal more and more of it over time. Are there any other like major technical changes you need? Any major hurdles? Things like finding a way to have interconnect, or are there any other things that you're hoping for that will blast this, accelerate its rate of improvement?
Yeah, one thing I'm really excited about, and I think underscores that we have a long term view of quantum computing in our approach, particularly, is in Madison, we have what we call the error correction testbed, or ECT, at our
Hmm.
Madison office. And this is related to Professor Mark Safman's work at UW. He's the chief scientist for quantum hardware at Infleqtion here, but also wears his professorship hat at UW. So the ECT, the error correction testbed, is our dual species testbed. And so that uses two different species of atoms to make up our qubits. And that gives you all kinds of advantages as you move further into the fault tolerant regime. So that's something I'm excited about, looking forward to future progress in particular. So in the dual species approach, you have some data qubits. You use one species as data qubits and the other as ancilla qubits, and that unlocks all kinds of advantages. So I'd look to the error correction test bed, some results coming out of there. Maybe not in the near term, but in the coming years, I think that there will be a lot of fundamental breakthroughs there that'll enable further progress on things like Shor's.
And that's rubidium and cesium, right? The two.
I believe so. Believe so.
Yeah, that's great to have that immediate test bed. And of course, Chicago is a great place for any concept of quantum networking. All that's underway right now. That's sort of like the whole thing that they're trying to develop there, right? It's this
Yeah.
idea of like quantum networking.
Yeah, there's actually quite a big network going from not just Argonne to U Chicago down in Hyde Park, but I think there's a network being built out by a company called Quantum Corridor in Indiana. So it's actually all over Indiana too.
Yeah. Before I let you go, I know you also had some work with clocks at Infleqtion, right? And that was, I believe, a government contract as well.
Yeah,
And with networking, do you have any plans on making the quantum sensing side connect to the quantum computing side? Is there anything like that that's sort of in the roadmap too?
yeah, we've definitely looked at different integration points in our portfolio. So as you know, we do not just clocks, but quantum RF receivers
Hmm.
and inertial sensing, things like that. And we're always looking for ways that one part of the portfolio can tie in with another part. So my favorite example of that is with quantum RF receivers, actually. So using this quantum inspired machine learning, contextual machine learning that I mentioned earlier, to more efficiently do signal processing with RF receivers. So that's my particular favorite one. But yeah, we've looked at other integration points too, clocks and computers. Where we've looked at how clocks can help improve the performance of quantum computers for neutral atoms, for trapped ions even. So definitely something we're looking at.
Great. So I'm excited to see what comes next. And I hope you guys get to crack encryption first now.
I guess me too, but not in the
Yeah.
again, we think better us than someone else. So
yeah.
and
I think that's a sentiment a lot of people can agree with.
definitely.
So Peter, great to have you back, and we'll be watching to see what comes next.
Yeah, thanks for having me on. Really appreciate it.
That does it for this episode. Thanks to Peter Noell for joining to discuss Infleqtion. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.